Thank you for everybody waking up on a Saturday morning to be here, but it'll be well worth your while. Our first speaker is Anna Busic, and she is right now at INRIA, Rocancourt. She does work in markup chain simulation, performance simulations of communication networks, and she did her doctorate at Université de Versailles. And she also is a member of the computer science department at l'École Normale Supérieure in Paris. She also doesn't want me to tell you that she won a best tool paper recently, but she did. And without further ado, thank you, Anna.
Thank you. I'll talk about dynamic matching models, and also I'll try to give you some history about this model and how I get interested into it, and how I started collaboration with Varun Gupta, Jean Meres, and Sean Mine on this topic. So it all started in 2009 in Paris during Stochastic Networks conference, when during some coffee break Gideon Weiss started describing to Jean and me the model that he recently got published. And so the initial application that they were interested in was housing social like housing assignment. So you have different families that arrive in the system, and they can write some requirements they want, like maybe selection of neighborhoods they're willing to accept, and the surface of the house, maybe some facilities like for kids or grocery stores and nearby. And on the other hand, you also have houses that become available and that have some of given attributes, but not all of them. So it looks a little bit like multi-class queuing systems, where you have rivals in the system, like families can be thought of jobs that arrive in the system. So they have different classes according to their requirements. But then you can't really think of houses as servers, because once they get assigned to a family, they disappear from the system and they're no longer available for the next family. So in some sense, you have both families and houses that arrive in the system, and then the service is actually when they get matched and then they both depart from the system. It is also similar to the huge literature on matching models, but all this previous work was considered in the static setting. So the idea was then to introduce a new model that is some kind of mixture between matching problem and a queuing system. So it's a multi-class queuing model where we have supply and the demand that play symmetrical roles. So there is no notion of service in the system. Okay, so here is a picture of one example, also called NN model. So you have here demand of 3 different kinds, and here there is supply. The simplest version you can think of is in discrete time system. So the arrival process is considered as IID, but with the constraint that the amount of demand and supply is equal at every time step. So there are so, as I said, service is actually the matching between demand and supply, and we assume that the matching happens instantaneously. So they just get matched and disappear from the system. The ones that cannot get matched are stored in buffers. So you have one buffer for each demand and supply class. So assume the initial state is this. Then you have one arrival, one red arrival, and one, what is this, purple, in the system. So you can see that this supply here can get matched only with the green class, and the red one cannot get matched, so the next state will be this. And of course, here now, for this supply class, you have choice whether you will get it will get matched with green or with red demand class. So in order to completely describe the model, you also have to specify the matching policy. Okay, so maybe this constraint of equal quantity of demands and supply seems a bit artificial. There is another. Can
I just ask, is that equal then every time, or this equality, or is this equality of statistics?
So it's actually equal at every time step.
The actual realization of the
And I will consider the simplest version in the rest of the talk, where at each time step there is exactly one demand and one supply item that arrive in the system. So you can consider this as a very artificial constraint, okay? But there are actually some possible implications in healthcare that really have this constraint. Here it's an example of a kidney donation program, where if you need a kidney and you don't want to wait for the classical procedure, you can actually find a family member that is willing to donate a kidney, it's a living donor, but you are not compatible, so they will get into the system and hopefully find a match. Okay, so okay, but when I started working on this, my motivation was just a very interesting queuing model that has similar flavors to things that I know, but at the same time, it's much more difficult than I first expected. So initially, Guido considered the FIFO policy, because in the housing application, since it's a social program, it's very it would be very inappropriate to leave families and to wait for the house while there is empty house sitting there, and so people would actually complain a lot, and there would be it would be a huge deal to do some kind of reserves. But then what happens is that you get very nasty state space, because you have to keep track of everything that is unmatched in the system, what is exact order of the arrivals in the system. So it's not really easy to deal with. And in their initial paper in 2009, they were able to, they defined the problem, they were able to give necessary stability conditions, and solve the problem for very special cases, like N model, where you have two classes of demand and two classes of supply, and they form N bipartite graph for the matching. And some other, like similar examples, where basically there can be only one type of unmatched items, like one type of unmatched demand, or one type and one type of unmatched supply that stay in the system. So you get just one-dimensional Markov chain, and that's very easy to solve. But other than that, it was just impossible to say anything about it. I'll come back to the FIFO model by the end of the talk.
That's a stupid question. Possibly missed the boat question. So you've got this matching. So you have one set over here, same set over there. You're trying to match. And this is the baby problem. And then if you actually look at the matched graph, it's a cycle. So everybody, you can't donate to yourself, for example. So what is the? I want to understand what the graph looks like. This bipartite matching graph, because there are different ways to do it.
Okay, so.
And then anybody can help me, because it's going to be a very stupid question.
Show the video.
The video? Okay, so here. So there are two different, populations of queues. One is demand and the other is supply, or whatever you want to call them. For instance, here on one side we will have families, on the other side we will have houses. So I don't think it does that answer the question, or?
I think, but go ahead.
Well, I think it's because your performance here will be the content of the queues. So you've already got too much supply of a certain sort. So in this case, she has supply of yellow houses, but nobody wants yellow houses yet. She has demand for green and red. There's nothing available for green and red, and so I presume you're going to retain, even though you have one unit of stuff arriving each time, it's going to appear uniformly in a class or something.
So
yeah, I imagine like this is right. So supply and demand come at the same time. They're coming, and they either get matched immediately and vanish, or they whatever doesn't get matched based on this graph, because it says what population they just get stored in the queue.
But you have a decision to make as well, right?
yeah. So for instance here, when like maybe this is the example of. So this one will get matched immediately with this because there is something sitting there, but this one will just stay here.
So the graph
and this is this is possible matchings that you can make.
But you have to tell us that actually how you resolve ambiguities, because you have something appear at the very bottom right-hand queue. It could absorb a green, or it could absorb a red.
So for the FIFO policy, it doesn't matter, because you will have also the information who arrived first, and you will have the exact order of the arrivals of.
Care about FIFO for both the demand and the arrival.
Yes.
In the for demand, but not for the supply, right? Because it's just this house has been sitting around for a while, so I have to give it to you.
Well, it works for both things. You don't want families to sit there because they are without house. But house, if the house is sitting around and there is no family for it, you have to pay taxes for it. You have to pay someone to maintain the place, so it has cost as well. I mean, maybe it's less important than the cost for the families, but.
If I have two houses that you can choose from, I can only give you one, so one of them is going to incur a cost for me. So it just seems like an asymmetry.
Yeah, so that's one of the things that maybe the model is not perfect about, because in real application you will have some kind of asymmetry going on. But you can also you can also to some extent encode this in the cost function that you will put on the buffers. So you can have much higher cost for families and very low cost for houses. So you don't really care about. If there are lots of...
having the resources and being in demand for them. For example, book exchange, right? Where your user books, so basically when you get into this pool, you can give away, you share, like a sharing model, right?
Well, I think that's what you're doing with the kidneys.
Yeah, exactly. So.
I'd rather read a romance novel. I really need it.
Yeah. So yeah, any ideas on applications are very welcome because it also can motivate some variants of the model that I haven't thought of.
I think also if you're looking at peer-to-peer downloads, because you have these requests coming in.
Oh yeah.
So people have a lot of.
It's not so severely managed.
Different
Well,
pieces,
you're allowed,
right?
you're allowed to normally sort of some form of asymmetry, and then it's also,
But it has the same flavor of difficulty in itself, because like why this is kind of it's a queuing model, okay, but at the same time it's a very unusual one because usually in a queuing system, more you have things sitting in your queue, the worse is the situation is for you. So you want to have queues as empty as possible. Here, having things sitting there, like having this green thing and two red ones sitting here, is actually good for this new arrival. So it's not really clear what is best situation for you, and you have to have some reserve sitting there, but if you have too many of them, then you're unhappy. So what to do? Okay, so I'll go back to. So first thing was that initially we thought that FIFO could have like the model under FIFO policy could have product form. So that inspired us to study this. And after a couple, I mean, at that time I was a postdoc in Paris working with Jean. And so Jean is expert in proving product forms for queuing systems and for all kinds of other combinatorial models. So we were very inspired and we worked very hard, and all possible, after 2 months of my postdoc, all possible conjectures we had proved to be wrong. So, okay, what to do next? I kind of got attracted by the model, so I decided, okay, why are we so stubborn about FIFO policy? Okay, maybe it's an interesting policy, but can we say something, whatever policy you can think of? So, okay, so we still have a matching graph. We have joint probability measure for arrivals, and we have some matching policy. In the system, it doesn't have to be FIFO. However, I will assume that the policy depends only on the current state of the system, because I want to keep it Markovian. And since I don't want to have nasty problems I went into with FIFO, I will try to study only the policies that depend on the total amount of items per queue. I don't want to track the whole words of arrivals. Okay, so also notice that at all times, not only if I assume that there is an equal amount of demand and supply that arrive in the system, then this will also be the case for the queue length, I mean, for every time step. Okay, any questions about the model?
So you're going to have a deterministic decision process, presumably. It's just a function of your current state.
Oh, it doesn't have to be deterministic. I will allow randomized policies as well. That's a good question.
So by only recording queue length, you're throwing away all delay information. So I can have a short queue that just hasn't been served for a very long time. Right? Yeah.
I just prefer to be able to just decide on the queue length only and not additional information, because yeah, it's but some results are still valid if you take 5 or whatever, like whole information on your arrivals. Just the most important assumption is that decision depends only on the current state, whatever that is, like only on what happened until time t, and the arrivals in the system that just arrived. And okay, so one example of such policy is like priority policy. Maybe like if you are a family, maybe you prefer just one given neighborhood, and then if there is not such house, maybe you are willing to move a bit further. But if you have choice, you will always choose your favorite neighborhood. Okay, another policy is just random. Pick a random queue, or according to the amount of items in the queue. And we'll see some other later. Okay, but so first question was, can we actually say something about stability of our Markov chain under various matching policies? Stability in the sense of positive recurrence of the Markov chain. And well, there's some interesting observation around stability that can be made only by looking at the matching graph and the support of the probability distribution for the arrivals. So I'll call that arrival graph. Well, first of all, no matter what policy you consider, a necessary condition for stability is that for every subset of demand classes, the arrival probability of this subset must be strictly smaller than what can the supply that can get matched to this demand subset, symmetrically for supply. So this is very similar to Hall's marriage theorem. So it's just instead of having inequalities, here we have strict inequalities because of stochasticity in our case. So the first question is, okay, can I actually check this? Because it's very nice in queuing systems, but usually I have 2 queues up to maybe very limited amount of queues. And here I have potentially huge number of queues, and checking these conditions for every subset of demand class and supply class. Actually, you only have to check subsets of demand class, because for every supply subset you can find the demand subset that gives you the same condition. So the answer is actually there is using network flow arguments, you can check these necessary conditions in polynomial time. And this complexity here is a complexity of max flow algorithm you decide to use. So it's okay. So let me give you just one idea, because it's not really straightforward, since you have strict inequalities here. Max flow doesn't like strict inequalities, so if I would just have inequalities, it would be obvious. But okay, first, I don't know if everyone is familiar with network flows, but here is a little figure. So I assume my network consists of one source and one destination node, and then my bipartite matching graph. And for arcs going from source to demand classes, I will set the capacity to be the probability of arrivals of demand class D. Similar for the supply. And then on the arcs between demand and supply classes, I'll set infinite capacity. In that case, there is just using max flow min cat arguments. There is this. You have this first result that is really straightforward. But then, in order to go from inequalities to strict inequalities, you need to make the following observation, that there is a flow of a value 1 that is strictly positive, meaning that it, on every arc from D to S, we have our flow will have strictly positive value. If and only if these conditions, necessary conditions for stability, are satisfied. Okay. Still not really obvious how to check that, right? But I don't know, like just the sketch of the proof is just use the fact that it's easy to construct the flow of value 1, but that will not necessarily have the property of being strictly positive, and then perturb slightly this this flow, but by adding. But combining it with with another network flow that is strictly positive, and this we will just take this with a weight that is small enough. Okay. So now when we have a characterization of necessary conditions in terms of network flow arguments, there is a nice verification argument algorithm we can come up with that uses as input the values that are not really explicit, but they are given as some value x plus some small value multiplied by some constant y. And so you can do addition, operation, comparison between these formal quantities, but you don't need to know what this small value eta is. By the end of, so you just run your max flow algorithm. It will stop in finite time, and then you can, when it stops, you can actually derive the value of eta for which this will be okay. So it's kind of a nice trick. Just don't know what this value is, but you can still run max flow on this problem. So, okay, there is a nice necessary condition. We can check them in polynomial time. But can we go a little bit further from that? So is that, okay, before that, there is just one example that I don't, I mean, how to say that? The idea is that I would like to find, just by looking at the structure of the matching graph and the rival graph, whether there is some kind of probability measure I can put on the arrivals such that I will get necessary conditions. For some models, this is not possible. So here is one example. Here is the matching graph. On the right, you have the arrival graph. So for instance, we cannot have one from the demand class and 4 supply that come together in the system. In that case, if I consider supply subset 1 and 2, then so 1 and 2 are over there. Then I have to I can have arrival of this type or of this type for 2, and the sum of these 2 is actually small or equal, and then this arrival, then the probability of this arrival subset 3 and 4, which will give us the contradiction of necessary condition for the demand set 3 and 4, because if you look at the demand set 3 and 4, the only supply classes that can serve it are 2 prime and 1 prime, and so their arrival probability is smaller or equal than arrival probability of the classes 3 and 4.
Can I ask a question just to clarify again something?
Okay.
Now so you had, your demand supply was just 2 parallel lines that weren't connected. So if I have 1, 4, 3, 2, is that not already doomed? Because I can, if I just uniformly put my arrivals. So I'm wondering, do you need some connectivity in the matching graph, or you need?
That's a beautiful remark, because I forgot to say that that my assumption is that the matching graph is connected. Otherwise, it's very easy. I mean, it's the only way you can actually have some kind of stability is that you disconnect completely into 2 separate problems, and you have then the assumption that the amount of arrivals and supply in each sub-graph are the same at each time step.
You somehow have to be able to push demand around the network, right? So without
exactly. Yeah. So just ask all kinds of questions. Okay, so it is for me it was intriguing that you can just by looking at the graph structure for of the matching graph and the arrival graph, you can actually see whether there is whether you can find a probability measure such that it will satisfy necessary conditions. So, and the trick is the following: take the matching graph and put the orientation on the edges from, well, this should be D here, from demand class to supply, and then do the opposite orientation for the arrival graph. So then put both of them on top of each other. This will give us a directed graph here. Is it clear? How did we get it? And then, if this, there is a probability measure mu such that it satisfies necessary conditions, if and only if this associated directed graph is strongly connected. So it's kind of cute because you just look at the graph structure. It's very nice to check, and you can see whether it can be. You can have arrivals that will be stable. Here?
Yes.
So here is the, on the matching graph, I will put the orientation from demand to supply. and here from supply to demand. Now I just put union of the two to get this. What?
It shows that you have to be able to push stuff around.
Yeah, exactly.
Can I ask, I'm anticipating something that I suspect you're going to tell us, is that, do you have an example where the necessary conditions are not sufficient?
Oh, no, it will come. It will come. It's policy dependent. I can just say this. Okay, so if this is the case, so now you have just you have to just look at the graph structure. Then you know if it's not strongly connected, just forget it. It's not possible to have stability. But if it's strongly connected, then on top of this, you also get the property that there is unique strictly connected component for the Markov chain. And this component is actually attractive. So starting from all initial conditions, you will go to this unique strictly connected component. Okay, so that's nice. That's the first step towards stability of our Markov chain. So, but now moving to from necessary conditions to actually some examples that are stable. Well, first we will try to have some sufficient conditions. And for that, I will look at, I will try to decompose the state space into facets that are defined by the demand and supply classes where there is someone sitting in the buffer. So on this picture, black circle represents queues that are non-empty. Then this double circle represents the classes that can serve the non-empty buffers. And then these circles here just represent the buffers that are currently empty, but at the next time step they might get full. So just, yeah. Okay. So for instance, if here there is a rival, and maybe we'll have a rival of like 2 and 3, then we will get this node as full circle, and I will get a double circle here. Okay.
So what's from your definition of a facet, like you're disallowing to have 2 non-empty adjacent queues? Am I reading that? Well, that's the D cross S minus E.
Sorry?
It looks like you're disallowing that I could have 2 queues, both non-empty, that are adjacent, that have an edge between them.
So that's
match if available.
That's like you mean I don't allow this one to be a full circle.
Like you, yeah, you wouldn't allow both 1 and 3 prime to have.
Yeah.
Okay.
Because they could get matched and just leave from the system.
Right. It's just not. It's not obvious to me. Maybe in some situations you should leave.
So you're anticipating. I love the comment. You're anticipating something that will come later. So indeed, at first, because we were motivated by this FIFO policy where you actually always would match, we studied the family of policies where whenever possible you would match demand and supply. Just would not allow some kind of reserves in the system. Well, just going from the assumption that was driven by this first initial application that families would get really angry if they see a house that is sitting there empty and they're outside and freezing, and yeah. So of course it would. I mean, we'll see that this is not necessarily what you want to do. But for now, well, I don't think this is actually interfering with this. Even if you would allow to have some reserves, you could always take like if you have two black circles that are that have an edge between them, then you could always say, okay, these are here reserves, but they could get matched instantaneously. So I will color them as double circle, because you can always just empty the system and see who is really there and who is there as a reserve. But it's not, yeah. But assume now, for now, that you have this constraint of the policy that that does not allow things sitting there if they can get matched. So the sufficient conditions written here are just obtained using a linear Lyapunov function and here you can, like if you get arrival of demand from double circle and supply from double circle, you will have -1 on your total queue length. And so in these cases here, you will have +1. So maybe like +1 in the number of unmatched pairs that I consider in the system. So it's sufficient to just count the amount of unmatched demand or supply. They're always the same. And then you have this intermediate case where if they can get matched between them, then you will get 0, and if not, they will contribute as 1. And so that explains this part here. But the thing is that these sufficient conditions are obtained by considering necessary conditions only for the saturated facets. I said thing a bit wrong way. Let me just explain. I don't know if this is really important, so let me just say that you can actually come up with some models that always have this, that always verify these sufficient conditions. So they're always stable, no matter what policy you consider. On the other hand, you can find example in which this set of sufficient conditions is empty. So I didn't say anything for these models. So they are like both extremes, which are not really interesting because it doesn't give me any information. I want to try to find some complicated system in which I will have a non-trivial stability region. And for that, like if we look at this NN graph, then the assumption is that I have product arrival measure, and then the arrival probability for the first class is denoted by X, the second class is Y, and then here in yellow you have sufficient conditions for stability, and then in this red region, well, you don't know for now what is going on. It depends on the policy, and this whole triangle gives necessary conditions for stability. So there are two questions we might ask. Is there a policy that always that is always stable in this triangle. And the second question is the policy that for which there is a point here that you can prove that the system is unstable. And so for the first question, the answer is match the longest policy that can be seen as max weight policy, where the weight is the number of items in each queue. And so match the longest has maximal stability region, and it's usual argument of quadratic Lyapunov function. But we weren't able to prove it directly for match the longest. We had to come up with some randomized policy that was easier to analyze, and we can show that this randomized policy is stable using Foster-Lyapunov criterion, but then match the longest is also stable as it minimizes this quadratic Lyapunov function. Okay. So on the other hand, if you take priority policies, or probably the most stupid thing you can do, match the longest, match the shortest. Sorry, let's just look at the queue that has the least amount of items and just take that. So of course this will kind of intuitively be on the opposite side from match the longest. And so for priorities, instead of like class 1, instead of serving the supply class 3 that has only one as possible match, will give priority to class 2. So in that case, you can, remember this was this, we want to find a point here in the red region that is unstable, and here is the example, and the proof is very, yeah, it has lots of epsilons in it. So I'll just skip it. But it's interesting because it's usually not very easy to prove that something is unstable. So it's, there are some nice tricks behind. And this is just empirical results. So it's, we were able really to find points that are unstable, but this is what happens for match the shortest. Okay, so back to the question, why on earth would we match things all the time? So, well, this is now the part that is joint work with Sean. And so after proving stability, I was frustrated because, okay, there are policies that are always stable, that are policies that fivefold, so you can prove using fluid arguments that is always stable. In the meanwhile, Gideon and Weiss and Ivo Adan managed to prove that some function of fivefold policy, of Markov chain for fivefold policy actually has product form solution. Therefore, not exactly on the same state space, but on the slightly modified state space, you can have product form solution. Therefore, also it's it was easy to check that it has maximal stability region. So you have two different proofs for that. But then, which one is better? I mean, you have these families of policies that are stable. So which one to choose? And sometimes you actually know the arrival rates. Maybe you can do better than just doing max weight in that case. So we considered average cost criterion, and just let me remind you the Q dynamics. So this is arrivals at time t, and this is our matching policy. So that is also constrained that we can only match things that are in the matching graph. And we have integer constraints, of course, on the matching sequence. So we consider policies that depend both on the queue length and the arrivals. So I will slightly change the representation of my state by using the sum of the two, and I will search the policies that depend on x of t. So the state space for this process is also constrained by the fact that you have the same amount of demand and supply items in the system. Okay, so why this this model is actually so hard? This became obvious when we started to ask ourselves the question, what is the workload? Like, it's a queuing model. There should be a workload process for this thing. Okay, so but it's not obvious to say what it is. It's as I said, usually more items you have in the system versus it is for you. Here it's not the case. So what's the workload? So we define the workload vectors for each demand class, demand subset, to be as the sum of all the items that belong to the class, to the subset D, minus everything that can be matched with this demand subset. Okay, in some sense, all these constraints from necessary conditions are actually elements of our workload vector. Okay, so it makes sense, right? How close you are to the necessary conditions for stability. So written in this form, if we have arrival, well, slight change of notation. Arrival process AT now is, I will denote by alpha the mean arrivals. Well, it was mu on the slides before, sorry for that. And then necessary conditions can be rewritten in this form. Is that clear? And okay. So why we call this workload? Because it's very consistent with other queuing models that we can think of. So if you look at the fluid model, then we will have in the this product here will actually give us the time to reach 0 for the fluid model, starting from initial condition that is given by x. Okay, so it's kind of how long it takes to empty my system if I start from a given initial condition. So it makes sense, right? It's to call this workload. However, this however, this workload here is a bit weird in the sense that it can also take negative values. Remember, workload is defined as amount of demand minus amount of supply that can get matched with it. So yeah, this shows why this system is not really typical, because usually we have workload that can only be positive. And you don't want workload to be negative. That means that you're paying some kind of storage cost for the other, for the supply on the supply side. We will look at into the heavy traffic setting, where at least one, and we will be interested in the case where exactly one constraint is very close to the boundary. Okay, and so I guess I'm slightly out of time. So we will fix one workload vector, and then you can just look at this dynamics of the for the workload process. But notice that it can actually can have increments that are at most minus delta in like expected value, where I actually dropped the subscript D because I will only consider one subset of demand. So when is this bound achieved? It is in the case where we don't allow the wrong matches to happen. We only allow a supply set that can be matched with D to sit there and wait to get matched with D. We don't allow what we'll call cross matches. So in some sense, in the queuing system, you have idling process. Here, idling means getting matched with the wrong class for our workload vector that we consider. So as long as you are sitting there, not doing anything, it's not idling. Okay, so it's just weird way of thinking, but it works. So in order to get some interesting policy, we will just look into workload relaxation. So in the sense that we will just ignore who is actually present there. We will only consider the value of the workload for the demand subset we are considering. Okay, so this gives us this dynamics. In the original system, it's not always clear that we can idle. We just remove this constraint here because we don't consider the actual state, just the value of the workload. And given a cost function C, then you can come up with a state X such that the workload is W, and then you have a bunch of these states X such that they have the same workload, and you just take the minimum of C of X for all these state X, and call this effective cost. It is piecewise linear in our case, and for this, you can use then results from inventory theory to show that the optimal policies for this kind of systems, that is once again relaxation of our original system, is they are of threshold type, and so you will have some threshold value above which you will not be allowed to idle. Idling means cross matching, okay, matching with wrong class. Okay, and you can actually compute the value of this threshold as well. Then this is one example. Do I have any time, or I think I'm a little bit above? Yeah, so I might just. Okay, so. This is just one example. So this is the cost function on the on my buffers, and which gives the effective cost here. I don't know if it's. Well, I'll just go to here. So for the effective cost, what you actually look at is, given the value of the workload, you look what is the state that minimizes the cost value. So if your workload is strictly positive, then for this, I mean, the workload vector we consider is given by demand class 3. So if the workload is positive, then this supply class will be empty, and actually we will have just, so we will have what? You will have, since demand class 3 is positive, we will have this queue that will be non-empty, and on the supply class, this one here. So this is how you can compute the value of the effective cost. And similar for the workload, under the case when workload is negative. But so I'll just give you the results. So you can compute this threshold value, and this is the average cost for the threshold policy, and so above the threshold you don't idle, below the threshold you're allowed to idle, and otherwise you just do max weight with this cost function that that we consider. So this gives this. But then already this gives better result than just standard max weight that that consider. I mean, it's weighted by the cost value. Okay, I'll skip the second example. And now the idea was, can we find some function h such that if you look at the h max weight policy, it will have some very good properties. I mean, can we derive some, can we have some guarantees on how far from optimal we can be in using this class? Because just taking the max weight without doing any kind of checks, you can just by using the threshold for idleness, you perform better. So can we find something that is even better than that? Well, I'll go directly to the conclusion. The answer is yes, and you can actually get asymptotic optimality in the following sense. Under some assumptions on the arrival process that I won't go into the details, but just we consider a family of arrival processes such that they are closer and closer to the limit of I don't know if delta goes to 0. But it means that you are closer and closer to the constraint that is given by necessary condition for this workload vector. And you need some additional technical assumptions. But one of assumption that is interesting, you must be able to idle. In some sense, there must be in the arrival process, there must be a way to do a cross match. Under these assumptions, you can show that there is H max weight policy that is not very nice to see. Sorry, Sean. For which we get bounded regrets for. So there is the average cost under this H max weight policy is yeah, it's I don't know how to explain that. I hope it's clear. I just explained what these stars are. So the eta star is the optimal solution for the original MDP model. This is hat is the optimal cost for the workload relaxation that I showed you before. And what is important that this factor here does not depend on the value delta that is going to 0. So you normally would expect something that that would depend on 1 over delta or something like that, but not or some logarithmic regret or something like that. But we actually get bounded regret. And then this thing here is the optimal cost for the diffusion approximation for the relaxation processes. So it can also get you can get closed form for that. Okay, so some final remarks. There are this. I mean, can we actually get some performance bounds? That would be nice. But also, like for like various policies, not necessarily. I don't know. It's something that I like to study, like how you can simplify maybe the model and get some bounds for Markov chains in general, but so here it's very complicated. I don't have any results yet. And so in the approach by workload relaxation, we only consider the case where you have one workload vector that is critical. What happens if you have more than one? So there is not one that is much like that is really critical, but maybe 2. And something that I started looking into is with Jean Mérès as well as how, like, what if you relax this restriction that you have bipartite graph, but you just have a general network and you match the you do matching on the. I mean, you have some kind of connectivity graph, and you just can have matches on according to the edges in the connectivity graph. And here is the related papers, and maybe I'll just mention that. In the meanwhile, we also managed to show that for a first-come, first-serve case, we have some sort of reversibility that finally explains the product form results that you can show that Adan and Weiss were able to show by just guessing the solution for the stationary distribution. Okay, and like this, these models from like constraint queuing networks and models for switch are actually quite similar to this matching model, but in some sense there are some things that make them more difficult and some things that make them simpler. Typically in these systems you have some kind of monotonicity property that break down in this model. So thank you.
So suppose that you do the reverse of the matching, so that you put edges among states that are not compatible. You know how you do in scheduling, you're finding stable sets, so like your facets. There, would be kind of your dominant. You have what they call saturated facets.
Yeah.
Right. So those
that would be
your dominant stable sets. And then you're just looking at all this, you're looking at the polytope of all your stable sets. Might that be a way of getting around the issue of the fact that you have a single flow? Because then you could have multiple class, you wouldn't need to be able necessarily to move stuff around. You could have then, for instance, suppose you just had a bunch of parallel ones.
Yeah, I'm not sure I understand.
So if you look at each, you basically have like the dominant points, right? Like you could always just schedule among those. Like suppose you had a really stupid policy, which is just fill up the queues like crazy, and then empty them according to a schedule, which would be going among these maximal sets.
But so I guess what I don't get is that how I can use these dominant sets in the complement graph for the matching in because these are exactly the ones I cannot match.
Right. So you just it's the same representation. It's just you're looking at the stable sets and you're looking at the polytope of all those, right? It's the same thing. It's just so I guess what I'm asking is, so people look at stable sets and they look at those polytopes of the stable sets. And can you actually match maybe your model to theirs? Is there a commonality?
So, like in the constant queuing networks, this is the way you do things, because you just schedule the independent, maximum independent sets, or and then so I first thought this would be the way to prove like at least for max weight variance. But what is the problem here is that like what I called monotonicity property in these models is that when you take a subset of this independent set, this is no longer independent set in my case. And this breaks down these ideas of convex hull of independent sets. So it's that's why I got also intrigued by this, because it's So it was really so it's there is no monotonicity in this sense. So it's kind of, it was, but because I guess there is some other variant like this workload process is very useful, and so I first thought in the terms of independent sets and like links with because it didn't work.
Just wondering about how large backlogs build up, right? So one of the ways you could imagine is if you don't tell me your policy and you just give me your arrivals graphs and your matchings graph, if I kind of dump things in one box over here and one box over there and they can't cross match, if I keep them separate, then I'll get a geometric tail, right? Because I just have to figure out from all of the places where I can dump them, where could they not communicate, if you know what I mean, and then I'll get a geometric tail. But I was just wondering if that geometric tail could be worse dependent on your policy, because your policy might allow you to dump stuff where you could probably serve them, but you choose not to, because you're deciding you're not always matching. So I mean, I don't have an answer, and maybe I'm wrong, but I'm just wondering, how do bad backlogs, can your policy make the likelihood of bad backlogs even worse?
I guess this is really policy dependent, but this is typically like for instability proofs kind of.
It's more about the nature of the tail, like the tail has to be geometric. If overall policies, I'm sure it's geometric, because I can just.
Are you asking? can get worse than that. I don't know.
I guess it's in part related to, I wonder if there's a constrained alternate of your problem where you can say, given I'm not going to be a total idiot, what's the worst policy I can have? Because you would imagine state housing agencies are probably certainly the one in Ireland, I would imagine. So,
I mean, definitely like with this, the kind of policies looked at the end, and you're tracking sort of a relaxation where you know you've got the death geometric tail.
Right.
And then for some other policy.
Can you do the inverse? I mean, trying to. Probably, but I don't know what you get.
Maybe it can be worse.
Yeah, I don't know.
But the geometric tail, you would imagine, is a result that's a very low-hanging piece of fruit.
Yeah, well, you can see that there. You know.
So it would be interesting just to, be sure you can.
And by the way, just one of those weird technical conditions, back to your point again, that when delta equals 0, it's still connected.
Right.
You know, if when delta equals 0 is not connected, well then.
So you want
basically you can ignore it. You can just pretend they're two different queue networks. You know?
Right.
But it's like technical condition, because if you have separate two queuing networks, then it's simpler.
Yeah, but
so it's.
But they're still connected to some extent, just may not be.
Yeah.
The connectivity between is 0. And in our case,
it's just painful to.
Forget the fact that connected at all.
I see.
Yeah, exactly. So exactly, just
That's
and
interesting.
in that case, the heavy traffic isn't heavy; it's bounded
that's why I thought it's kind of easier, but you can't detect it by what we are doing. So it's.
Yeah, but it's a variant of what heavy traffic is, right?
It's
really not clear what your traffic is.
At first, that's like a really artificial assumption that you could always cross match, but then realize that if you don't have that, it's nothing to say.
Well, it almost feels like the appropriate heavy traffic limit should be something to do with a sequence of matching structures rather than anything else, you know? Slowly disconnecting them would actually be heavy traffic.
Well, that's what's happening here, though.
Yeah.
I mean, no, disconnected.
No, it's not.
Yeah, no, that's
You're
not what's
matching
happening.
the spaces.
No, the battery has to stick. If it doesn't stay connected, then it becomes
Can you
falls apart.
decompose it into a bunch of connected ones? Is that
But
easy to do?
that's the thing, yeah, but it is easy to split the
Is it?
disconnected pieces.
But it depends what you are doing. I mean, if it's if you have if your network is slowly decomposing into two parts, but you still have variables that can come in like in either then you are dead. It's
forgot about that.
then you lose stability. So
You lose stability.
yeah.
Oh, I forgot about that.
Two parallel lines is enough to kill you, right? Because just the randomness can make it so that that's why they don't need your strict.
You'd have to have.
But wait a second. Can this occur if you have uniqueness of the you have the uniqueness of the workload I mean, under the assumption of uniqueness of the critical workload vector, I don't think you can decompose the network into two pieces like that, because then you would have another workload vector that would be critical as well. I'm not sure about that, but it might be. But I mean, you can always consider what happens if you have two critical workload vectors and then you're stuck. So.
Any other questions? All right.
Thank you.